Hello everyone, this is video 3.3. We're going to be looking at the standard algorithm for addition and subtraction. I'm just going to warn you now, this is probably going to run a little bit longer than the average video. I try to keep these at about 20 minutes, but there's a lot to cover in this topic. And it's a pretty foundational topic for what we're going to be doing, so I try not to rush through any of them necessarily, but I want to make sure that we cover this in sufficient detail. So I'll put the running time in the title of it, so you'll probably know this before you hear me say this. But there's a reason for this taking a little bit longer. Like I said, there's a lot to cover. So let's get to it. So we're talking about an algorithm. It'd probably be helpful to define what an algorithm is. An algorithm is a step-by-step process for solving some sort of problem. Now, that's a very loose kind of definition. There's a lot of things that go into an algorithm that we're not going to talk about in this class. There are certain characteristics that an algorithm has to have to technically be an algorithm. But I just want you to think about this in the same way that you would think about like following the directions to bake a cake. So you flip over the box and you read, go get the milk, go get the eggs, go get this, go get the butter. So now combine this in this bowl. Now add this. Now do this. Now preheat the oven. All these little steps. You're reading that box. That's effectively an algorithm. It's telling you step by step what to do to solve the problem. And in that case, the problem is you don't have a cake and you want a cake. In this case, the problem is we want to add two numbers together or we want to subtract two numbers. But the idea is still the same. So it needs to be very clear. It needs to be very precise. We need to understand what's going on. So that's a very loose sort of definition of what we mean by an algorithm. I want to review very quickly this idea of grouping because it's going to be a really important idea for what we're going to be doing for the rest of this video and really the rest of this class. Grouping is a very key idea to what we're talking about, and we talked about base 10 blocks. We talked about the idea that we could take 10 units, and so if I had 10 units, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that they would group together and make one long, right? So we have a certain number of things in one place value, my ones place, grouping together to make something in my tens place. Now we're going to see later on that this grouping can be undone. We can do ungrouping as well. So there is an exchange that can take place from one place value to another, either grouping things together into a larger place value or by ungrouping things from a larger place value into a smaller place value. This is a really fundamental idea, and if you want to teach addition and subtraction without really establishing this idea of grouping ahead of time, you're going to find yourself swimming upstream for a lot of what you're doing. And I know that a lot of teachers will say, well, I don't have time to talk about, something like that because this seems extraneous, and it's not. I mean, it's an investment. It's a cognitive, conceptual investment that you're making with your students. Because now, once they understand what grouping is as a process, you can call back to that idea and call back to that thinking as we go through. So I just wanted to remind ourselves what grouping is because we're going to see a lot of it. So let's look at an addition problem involving base 10 blocks. I put a link up online to where you can go work with some online base 10 blocks. I mean, if you happen to have a set of base 10 blocks laying around your house, I don't know why, but you could use those as well. Or if you wanted to, get a box of popsicle sticks or toothpicks and make your own base 10 blocks, quote unquote, you can certainly do that as well to sort of follow along. But I'm just going to draw these so you can kind of see what's going on. So the problem that we want to do is 165 plus 36. This is what we want to add. And so I'm going to model this using my base 10 blocks. So before I've gotten to this point, I'm going to hope that I've worked with students sufficiently to where convert 165 into base 10 blocks is not going to be a challenge, that they already know how to do this. There we go. Okay, so there's my 165. So 100, 6 tens, and 5 ones. And then I've got 1, 2, 3. I should make these be like roughly the same length. 1, 2, 3, 4, 5, 6. And we saw in the previous video that addition means I'm combining these things together. So I'm combining these two sets together. Here's my set of 165. Here's my set of 36. And I'm combining these together. And so that's what we think of for addition. So let's go through this process. So I'm going to look at my ones. And really what I want to do is think about that idea of grouping. When I combine these ones together, can I do a grouping step? And the answer is yes. If I count through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You know what? I'm actually going to do that in a different color so we can kind of see what's going on. So I'm going to do this in sort of a dark green here. So I'm going to do all of these together. And so they will group and make another 1. Just like that. And so now I've got this 1 left over, and he doesn't do anything. He's not gonna group with anybody, so he's just gonna be left. And now I can look at my tens place. I can look at my longs. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got just enough. So I'm gonna group all of these together, and they will come over here and form another flat. Do I have enough flats to regroup? No, so we're kind of done there. So now we can go through and look at our answer. So we had 1, 1, we had 0 tens, and we had 2 hundreds. So the answer is going to be 201. All I've done is combine these things together. I've used the definition of addition that we're combining sets, and I've used my definition of grouping that I know to trade up 10 things. How do I know 10 things? Well, it's right there in the name, base 10 blocks. I know I'm grouping 10 things at a time. So this is how I'd model this with base 10 blocks. We've talked about this continuum before of concrete to abstract. And this is pretty darn concrete. The only way that you would probably make it even more concrete is if you actually pulled out 165 little blocks and 36 actual little blocks and then went through all the grouping themselves. So if you just didn't even talk about place value at all, you actually use the quantity of 165. That would be probably way back. That would be back here. That'd be even more concrete because place value is an abstraction. So we're using ideas of place value. So it's a little bit abstract, but not an awful lot. The actual algorithm is going to be up here. So here's base 10, and here's my algorithm. And so what we want are steps along the way. So rather than just start at the algorithm and say, do this algorithm a bunch of times until you understand it, we're going to want to start back here, something concrete. And then as students understand this, we're going to take these steps until we get up to the algorithm. And then every now and then we'll take a step and a student will struggle, and we may need to go back for a minute. We may need to go back and reinforce some idea, or there may be something the student didn't understand that we didn't recognize that yet, or maybe the student didn't recognize yet that they didn't understand. But we're going to move back and forth in these intermediate algorithms. So these intermediate algorithms. And this is where a lot of the art of teaching takes place, of understanding where students need to be at any particular time and moving them forward as they can and then moving them back as they need. Okay, so we'll do the same problem with a place value mat. And so we've seen this idea before. Here's my hundreds, here's my tens, here's my units. And so we've got 165, I've got 36, and same thing, we've got that top set of 165, we've got that bottom set of 36, And we're just going to combine these together. So here's 10, and they form 1 here. And you can see this is even more abstract. We're moving toward the algorithm because all these pieces are the same size. So 100 is not literally 100 times bigger than a unit. These are all, we just use little chips, or we could use pennies, or we could use, use whatever kind of marker we want. All these show the same size. So this is a little bit more of an abstraction. These 10 trade up to make another 100. And then we just look at what we have on the mat. We've got 2 here. We've got none here. We've got 1 here. So we've got our answer 201 again. Not that much different than what we saw with the base 10 blocks. Again, it's just that little bit extra layer of abstraction as we move away from the proportionally sized blocks to the non-proportional chips. So now we can get to the actual algorithm. And so once we've reinforced it with something, this process should make a lot more sense. So I'm going to add the 5 and the 6. Well, this already is a question that you're going to get from students, and that's why we start in the ones place instead of the tens place. And you should have an answer now, because we group to the left. We don't group to the right. So it doesn't make sense to start on the left and move to the right, because then the groupings will be moving the other way. So once we do the 6 plus 5 is 11, so we have 11 chips, we know this is going to group over 1. And then this 1 is done. Nothing's ever going to change this 1. So we know that we're done. Whereas if we move from left to right, we may have to go back and revisit things as things group sort of against the grain of how we're working. Now, this is an 11, but I can't write 2 things here. And so this is a 1, and the other one is a 10. And so it belongs in that 10's place. If students have worked with place value mats, or they've worked with base 10 blocks, this idea of this 1 moving over into this new column is not going to be foreign. It's not going to be a mystery. They'll recognize that I had an 11, which is a 1 and a 10. And where do 10s go? And 10s go in the 10s column, or 10s become 10 shapes, which is really saying 10s go in the 10s place value, which is where they belong. It's the 10s place value. So now we can add 1 10, 6 10s, and 3 10s. And again, if students have reinforced, if we reinforce the students this idea that this is the 10s place value column, then they know that all of these are 10s. This 3 is really a 30, the 6 is really a 60, and this 1 is really a 10. And these add up to make 100. And so there's 0 10s, but there's 100. And then they add this 2. This idea of calling it carrying, I kind of don't like, because carrying doesn't really mean anything. It doesn't describe what's going on. I'm a much bigger fan of calling that grouping or regrouping than calling it carrying. I don't know what you're carrying anywhere. I don't know what's getting carried. We're moving 10s into the 10s column. We're just grouping. That's it. And so I think grouping describes a lot better what's going on. In terms of subtraction, it's a lot of the same idea. We want to make sure that we go back and think about how we talked about modeling subtraction with base 10 blocks before, and that we're going to be removing a set and not combining sets together. So let's take our fact family problem for what we just solved, 201 minus 36. Instinctively, you might want to make 201. You might want to model 201 like this, and then put a 1 over here, and then make 36. Don't do that. Remember, we're not adding these things together, right? So from my set of 201, I want to remove 36. So here's my set of 201, and now I want to remove the 36. So can I remove the 30? Well, no, I can't remove the 30 yet because I don't have any 10s. So how am I going to solve that? Well, I'm going to take one of these 10s, I'm going to break it apart. 8, 9, 10. And so now can I remove my 30? Yeah, I'm going to use my green again and get rid of this 30. All right, so now I've done the 30. Can I do the 6? Well, no, I got the same problem. I only have one unit. So I'm going to take another unit. This one, I'm going to break it. And so I'm going to break it into 10 pieces. And so you might want to draw a little arrow here to show that this flat became these 10 longs. Here, I'll put it back in green so we can see the work stuff is in green. So this flat breaks and becomes these 10. And then we can show that this long breaks and becomes these 10 units. So we can draw little arrows to sort of like, direct traffic and kind of see what's going on. You'll have to judge working with your students, how muddled this might get and how confusing these arrows might get. But we definitely want to do something to sort of like show how things are moving. And so now we've got plenty of units. So I could take these 6 and remove those. So I've removed my 30 and removed my 6. All right, so now I just got to look and see what I've got left. Well, I've got 100. I've got 1, 2, 3, 4, 5, 6 tens. And then we've got 1, 2, 3, 4, 5 units. So 165. That's it. The same idea of grouping, but in this case, we're trading down instead of trading up. We're breaking pieces apart, but we're still going 2 to 1. I mean, not 2 to 1, 10 to 1. So we're still trading things down. 1 of a larger place value becomes 10 of a smaller place value, just like we did before where we had 10 of a smaller place value became 1 of a larger place value. The same idea we can apply with the place value mat. Again, it's the same idea. 201 minus 36. It's just a little bit of an abstraction now of not having, again, the proportional size pieces. So hundreds, tens, units. And in case you're curious, the reason why this is usually labeled as a U is because if you label it as an O for ones, it looks like a 0, and that confuses some students. So a U doesn't really look that much like a number, not like an O does. So it avoids a little bit of confusion. So 201. So there's my 201. And the process and the thinking is still the same. I want to remove 3 from the tens, but I can't because I don't have enough. So I'm going to get rid of that. And that becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've ungrouped that 100 into 10 tens. And now I can remove my 3. 1, 2, 3 goes away. Now I need to remove 6 units. I don't have 6 units to remove, so I got to break one of these up. And it comes over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that 110 breaks into 10 units. And same thing as before, I can remove, oh, not 3 of them. What am I doing? 6. I got to remove 6 of these. So 1, 2, 3, 4, 5, 6. So get rid of those. And so I'll look at what I have left. I've got 1, 2, 3, 4, 5, 6. And then I've got 1, 2, 3, 4, 5. 165 again. The process, the thinking is very, very similar. Again, we just have this extra layer of abstraction, not using the proportional size blocks. So now we can get to the actual algorithm. We can get to the actual the speediness of it, and this is where you'll see a lot of people complaining about this type of math instruction, is they feel like, well, I'm supposed to use blocks for every single problem, and it's a real misrepresentation from people who probably don't understand what we're trying to do with new, modern, contemporary mathematics pedagogy. It's not that we bring the blocks in because we want to have students using blocks all the time. I don't want anybody trying to do their taxes with a bunch of blocks on their table. That doesn't make any sense. What we want, though, is for this algorithm to be supported by some level of understanding. That when you do the algorithm, you understand why you're doing it, that it makes sense why you're doing it, that it connects to something. And so if we've gone through those base 10 block examples, and we've gone through the or the placemat example, when I do 201 minus 36 as an algorithm, then it should make sense what's going on. I mean, it should make some degree of sense. So let's work through this the way that most of us learned it. So I'm going to take this 2. I see the first I got to do 0 minus 3, and I can't do that. And so I'm going to break this down. Now you might notice in addition we went from right to left, but in subtraction we go from left to right. And again, it's because we're moving in the direction of grouping. In addition, we're going to group up, and that's moving to the left, so we add to the left. In subtraction, we're ungrouping, we're breaking groups apart, and that moves objects to the right, so we subtract to the right. So if you've ever wondered why we add and subtract in different directions, or if you have a student that asks you that, that's the reason why, because these algorithms are dependent on the process of grouping and ungrouping. So I want to do 0 minus 3, and I can't, so I'm going to break this apart. Now, I'll tell you, a lot of students will look at this and they'll just see 20 minus 3 makes 17, but we're going to assume that we're doing this based on place value, because that 17 is not really going to work because of the 1 and the 6. So we're going to kind of try to keep this restricted to place value for right now. So this 2 becomes a 1, and then this 10 becomes a 0. Now, I'm sorry, this 0 becomes a 10. You might have learned this like this, where you just put like a little 1 right here. And you certainly can do that too. In my experience, if that gets confusing for students, then you kind of want to skip that and really just write what the actual number is. And so I'm going to write a 10 above it like that. That little 1 with the 0, for some people that makes sense, for others not. To sort of introduce this idea, I'm going to be a little bit more explicit than I normally would be. So the 1 is done. The 10 minus 3 is done, but now I got to look at this 1. This 1, I'm going to wait on this 1 right here. So now I got to do 1 minus 6, and I got the same problem. I can't take the 6 away from this 1, so I'm going to take one of these away, which means now I have 9. And that breaks into 10 more over here, which makes this 11. And if you go back and look at the previous slides, it's exactly what we did. It's exactly what we did. We took one of these 2 that left 1. Now, we didn't really say anything about what was left at the time. We just sort of left it there. But that broke and became 10. And then one of these 10 broke, and there was 9. And again, we didn't really say anything about the 9 at the time. But we knew, it's implicit. We had 10, we broke 1 apart, there's 9 left. And then those 10 moved over and made 11 total. The 1 that was there plus the 10 that we moved over. And so now we can remove 11 minus 6 leaves 5, 9 minus 3 leaves 6, 1 is just 1, and there's our 165. If you want a little bit more practice with this, I'll give you the problem 274 plus 89. And so I'll let you solve that as an addition problem, and then once you get, my goodness, once you get that answer, you can do the fact family problem for subtraction. Why did I write this as subtraction? 274 plus 89. Once you get the sum, you can go back and do that 363. Do the subtraction on that and make sure that you can use this algorithm in both ways, addition and subtraction. Make sure you know how to do it with base 10 blocks, number lines, place value match. The more models you have for this, the more flexible you can be in your teaching of this. So your checkpoint problem. I got a piece of wood that is 5 feet and 2 inches long, and I'm going to cut off a piece that is 3 feet and 8 inches long. So now, how long of a piece do I have? So you might be able to tell that this is the subtraction problem, most intuitively. You could do it as an addition problem. There's a fact family here, but we're dealing with groupings, and the reason why I chose this problem is because there's 12 inches at a foot. And so now we're grouping in 12s, not 10s. So just be thinking about that difference when you solve the problem. If you have any questions about this problem, by all means, please bring them to class. Email me, let me know. We'll get your problems answered. I'll get your questions answered. Thanks.